In this tutorial, I'm going to show you how to do a chi-squared analysis, which is what we do when we have categorical independent as well as dependent variables. Now, in the past, we have done analysis of variance. Let me enable editing. We have done an analysis of variance, which is where we have a categorical predictor or x and a continuous y or response, or we've done regression where we have a continuous y or a continuous x and a continuous y. Apparently I can't spell today. There we go, continuous y. So a chi-squared test is where we have a categorical x, much like we have with an analysis of variance, but we have also a categorical y. So how do we do this? How do we compare our treatments here? So I have a experiment where we raised oysters in indoor tanks, outdoor tanks, aquaculture tanks, as well as out in nature. And we're looking to see whether or not they live or they die, so we have a status of dead or alive. And the way that we first look at this is we have to first understand what we have observed. Okay, so what have we actually observed? And we usually set up a table much like this, where we count the number of dead that were grown in indoor, the number of dead that were grown outdoor, etc., and we fill in this table. Now, we can certainly just count the number like this, right? Just count the number of dead in indoor. That gets a little tedious. We could do a count if function, such as this, count if, and select the indoor tanks, and then we could type in dead, and that will count the number that are dead. Or instead of putting in the word dead like that, we just select the word dead up here, and it does the exact same thing. Another way of doing this is, of course, with a pivot table. So let's go ahead and do that. Insert pivot table, and let's put it into this worksheet right here. If we put oyster origin in rows and we put status in the values, this gives us a count of status. The problem is that it gives us a count of all of the aquaculture, a count of all of the indoor tank. And so what we would want to do is put oyster origin, or put status again in rows. And so that way it knows to divide this up into alive and dead. So again, what did I just do? I took the status and I put it into values because that is what we want to count. But I also put status into the rows, and this divides it up into alive and dead, and then we can just copy the values from here. And so let's do that. Indoor tank dead, it's right here, so 13. Alive is 8. Outdoor tank dead is 15. Outdoor tank alive is 13. Aquaculture alive is, or aquaculture dead is 4. Aquaculture alive is 11. And natural alive is 19 and dead is 3. Alright, let's double check that, make sure everything checks out just fine. So 19, 3, 11, and 4, outdoor 13, 15, perfect, and indoor dead is 13 and alive. Okay, perfect. So if we've done this correctly, then the sum of all of this should be in that column, and we drag that down to get the sums there. The sum of all of this equals 35, and we can just drag this over. And you notice that the sum here, the grand total sum, is 86, which means that the sum of either these two numbers should be 86, or the sum of these numbers should be 86. Either one, doesn't matter. The expected values are calculated based on what we would expect given the frequency of alive and dead. And the way that we calculate the expected values is equal to the number of, so for indoor dead, how many indoor dead should we expect? The sum indoor tank times the sum dead, divided by the grand total. Let's do that again. For alive, it would be the sum of indoor tank times the sum for alive divided by the grand total. And you know that you did this right if the sum here is equal to the sum above. So if this is equal to the sum right here, you know you did this correct. Once again, once again, let's do this. For outdoor tank, dead is outdoor tank times dead divided by the grand total. And again, outdoor tank times alive divided by the grand total. And you know you did this right if, when you sum them up, you get the same numbers up here. Aquaculture, sum times dead sum divided by, and I'll just type 86. Aquaculture sum times alive sum divided by 86. And again, let's see if we're right. Perfect. And finally, dead, or natural sum times dead sum divided by 86. And then natural sum times alive sum divided by 86. And let's see if we're right there. Sum. Perfect. And of course, the sum of the column should be equal here to 35. Perfect. And the sum of this column should be equal to 51. And the total, of course, should be equal to 86. Now we want to calculate the difference between this table and this table. And the way that we do that is by using this equation here, the observed minus expected squared divided by the expected. So let's do that. For the dead is equal to the observed minus the expected squared, and then divided by the expected. Now, just to play it safe, I always recommend putting these in double parentheses. All right, that way you are absolutely 100% sure of the order of operations, and you get this value. Let's do that again. Two parentheses this time. The observed minus the expected squared divided by the expected. Now, we don't actually have to do that every single time. Once we have that, we can actually just drag this down because all of the reference cells will carry. Now, when we add up all of this, all right, we're not really interested in adding up the individual columns here like this. We're not really interested in that. Instead, what we are interested in is adding up all of this together. And this value right here is called our chi-squared value. And this is the number that we are going to use to try and beat. So if we go to Google and we search chi-squared table, let's just click on this one. I guess this one is fine. Yep. So what we want to do is we want to search for our degrees of freedom in the table under the 0.05 column. Now, what the hell is our degrees of freedom in here? For a chi-squared table, the degrees of freedom is equal to the number of unique columns, or the number of unique responses, minus 1, times the number of unique treatments, minus 1. So we have 2 unique responses, so it's equal to 2, and we subtract 1, so we get minus 1. And we have 4 unique treatments, so 4 minus 1 is 3. And we just multiply those together, so 1 times 3, and we get 3. That's our degrees of freedom. So we go to the table here, and we look at 3, and we go all the way over to 0.05. This is what we say the number to beat. 7.815 is the number to beat. So let's record that, 7.815. Is that right? 7.815. Does our value beat this value? Is our value greater than this value? If it is, so if the calculated chi-squared value is greater than the table value, then our results are significantly different from random. Okay? And that's all. That's what a chi-squared test is all about. Let's do it again on this table right here, this practice table. So again, we have to record the observed values. So let's go ahead and use our pivot table. So we're going to put dog age here, put response here, but again we're going to drag response down to rows as well, and this way it gives us the number of unique instances for each one of these behaviors. So for puppies, which is down here, all right, we have to record the number that played, which is 7, sleep is 3, growl is 3, and beg is 2. For adolescents, play is 4, sleep is 1, growl is 3, beg is 7. For adults, play is 3, sleep is 6, growl is 2, and beg is 4. And for seniors, play is 0, sleep is 11, growl is 0, and beg is 4. All right, let's add up the sum there. Now this isn't terribly useful, except when it comes down to the expected values. What we really want is the sum of all of this, which is just going to be equal to the sum of these. But we'll do it anyway, because we do need to use it for our expected value table. All right, and now we get these values and 60. Now you notice here that we have an equal number of replicates for all of them, whereas in the oyster one we actually did not. We had an unequal amount of replicates, and that's totally fine. A chi-squared analysis allows you to have an unequal number of replicates. Let's calculate the expected values. The expected values for puppy are equal to the sum of puppy times the play for puppy divided by 60, which is this number right here. Now I'm going to do this fairly quickly, and the way that I can do this is by simply locking K4. And if I lock K4 and I just drag this over, then I get the correct values. And then if I do that times play divided by 60, and I again lock K5, just drag this over. And if I do this times this divided by 60, and if I go ahead and I lock K6 and drag that over, and lastly this times this divided by 60, or let's type in 60, and you see that all the values in the columns are exactly the same, and that's because we have an equal number of treatments. Oops, I did not lock it. I did not lock it, my bad. Let's do that. And you know that you've done this correctly if the sum of all of these is equal to the number of replicates. All right, and the sum for each one of the columns should be equal to, or sum for each one of the rows should be equal to 15. Oops. There we go, should be equal to 15. And the sums for each of the columns should be equal to 14, 21, 8, and 17. We can check ourselves there. There we go. Now let's calculate the observed minus the expected is equal to, two parentheses, the observed minus the expected squared divided by the expected. And what we're going to do is drag those all the way over here and over here and add them all up. This is the number to beat. Or sorry, this is the number that we're going to use to try to beat, right? So, oops. Let's go ahead and calculate the degrees of freedom. We have 4 treatments and we have 4 unique responses. So we have 4 minus 1 is 3, and we have another 4 minus 1 is 3. So 3 times 3 is equal to 9. That's our degrees of freedom. Let's go over to our table. Degrees of freedom is 9, so we go down to here, and we go all the way over to 0.05. This is the number to beat, 16.919. Do we beat 16.919? The answer is yes. Right here, we beat 16.919. Perfect. And that's all there is to a chi-square test.